Okay, it's great to welcome you here for the first of UWCSC's distinguished lectures for the 2008-2009 academic year. It's my great pleasure to introduce Jeff Dean. Jeff has had a peripatetic career. He was born in Honolulu. Somehow, after a period of time, he got his bachelor's degree from the University of Minnesota. That must have been a real wake-up, I guess.
Yeah. We moved in October.
All right, great. Okay. Worked for the Global AIDS program for a year, then came here for graduate school and got his PhD in 1996. Worked at the DEC Western Research Lab in Palo Alto for 3 years, and then went to Google in 1999, where he's a Google Fellow. Jeff, among many other accomplishments, won the UW College of Engineering Diamond Award a couple of years ago, our Outstanding Alumnus Award. So Jeff, it's great to have you here. Thanks for visiting.
Thanks, glad to be here. So, what I've decided to do today is to talk about what I see as a bunch of interesting problems that have been inspired by observing things we've tried to build at Google and seeing what kinds of problems crop up. And so on. So a typical user's view of Google is that we produce a bunch of products, some of which hopefully some of you use. And over time, that set of products has grown to encompass more and more different kinds of things. Our initial web search product has fairly different characteristics from an engineering standpoint than something that is maintaining per user mutable state like Gmail. So over time, this set of products has grown over time, and the way I like to view Google is that there's really a wide range of problems that span a pretty wide set of disciplines of computer science and other areas. In particular, ranging from pretty low-level hardware and mechanical engineering kinds of issues, like how can we build data centers? Given a lot of computers, how can you build efficient distributed systems out of them? What are the right compilers and programming languages to be using? Up to higher level issues like how can you build information retrieval systems that give users better results than the ones that we know how to build. All the way up to UI and kind of product design issues. And really a lot of the problems span many of these areas. So that's what I'm going to talk about. This is just kind of a sampling of problems that I think are interesting. I'm not necessarily saying that these are brand new areas. In a lot of cases, there's been great work done by academic and other industrial places already. So they're promising areas that have been explored a little bit, but we think that more exploration is needed. It's not really meant to be an exhaustive catalog of all the things we care about. There's lots of other problems that I didn't have time to fit into the talk. They're roughly ordered from kind of the lower level areas on that slide, like hardware design and so on, up to higher level things. And so without further ado, we'll start at the bottom. So one of the things that is really driving computation these days is the scaling of multiple cores instead of megahertz. Basically, the processor design community ran into a bit of a wall in terms of producing higher single-thread performance, and instead have moved now to producing more and more separate cores on a single die. So these machines are actually very, very fast, and that the number of cores is scaling very quickly. We see 4-core, 6-core devices today, and in the future you'll see 8, 32, 16, 32 on a single processor, basically. And so with the right kinds of problems, that's great. And fortunately, most of our problems have a huge amount of inherent parallelism, both very coarse-grained and pretty fine-grained parallelism. And we can pretty easily thread the kinds of computations we do for the most part. The tough part is that these machines have not really gotten more energy efficient. So as you look down the road, you see more and more of a sort of operational lifetime of a computer being consumed by the energy budget as opposed to the actual purchase of the hardware. Moore's law has done a great job in increasing performance, but has also increased energy usage. There's a real need for focus on energy efficiency, which means how much computation can you do per watt as opposed to per joule. So the second thing is that a lot of the energy efficiency work that has been done has been focused on sort of mobile devices like laptops, where you basically have an on mode, and then you have a really deep sleep power mode, where the device is, a lot of the peripherals are shut down completely. You can't really do much in that mode. You can power it up and start computing again. But in a data center environment, that's typically not as useful as a mode where you could, for example, compute at a half the rate with half the energy. That would be kind of a great thing to be able to do. And the reason for that is that you're very, very rarely completely idle in a data center. So what we have here is, on the right, a graph of the CPU utilization over time and a histogram of how often machines are at that level of CPU utilization. This is a sort of a 6-month longitudinal study of a bunch of machines in different data centers at Google. And what you see is you spend an awful lot of time in the kind of 0.2 to 0.5 utilization range. You're very rarely completely maxed out. If you were, that would be bad, generally. And you're very rarely completely idle. I mean, you're somewhat completely idle sometimes, but most of that time is in that big hump in the middle. So the problem with that is the energy efficiency of a machine. So the power usage when you're at 0% utilization is indicated by this green line. And so at 0% utilization, when you kind of shut things into this deep sleep mode, you're using about half the energy as when you're operating at peak. And so if you look at the efficiency of that, you're basically well below that green line in terms of energy efficiency. You really like to scale more linearly with energy efficiency than and have it intercept closer to 0 when you're there. So are there ways that we can design processors and other peripherals in a way that gives you kind of an energy proportionality for when you're at half usage, can you use half the energy? It's not just a CPU problem. This is a graph showing CPU utilization and energy usage of the different components in a machine. So at 100% usage, the CPU is about half the total energy in the system. And then there's a bunch of other peripherals, DRAM, disk, and other stuff that makes up the rest of it. And as you go down, first thing to notice is that the CPU is not really the dominant factor in system power, even at full usage. There's half of it is used by stuff other than the CPU. So it's not just a CPU problem. It's a whole system design problem. The second thing is that CPU usage drops off more quickly at low levels of CPU utilization than the other stuff. The DRAM and disks and stuff don't go into as good a low power mode as the rest of the system. So that's the current state. Here's 2 potential machines that take in energy and produce work. One is a typical desktop machine, 120 watts on average, and the other is a person. So this is the graph I showed you before, where the current situation is that completely idle periods, you're using about half of your peak energy. And unlike a human, who has a much larger dynamic range. When you're at rest, you're using only about 60 watts. When you're fully exerting yourself, well, some of us might be able to go up to 1,200 watts, but at least much larger than 2x of 60 watts. And that's a factor of 20 difference. If you could do that for machines so that instead of being on this line, you were much closer to this line, that would be a tremendous energy savings, especially for data center-based applications where you're often operating in this range as opposed to the fully idle or completely maxed out impact. And so my colleague Luis Barroso and Wolf Weber and Li Fen did a study looking at how much would be saved if we were closer to this green line as opposed to the red line. And for a variety of different workloads, you save an awful lot of energy, and you save a little bit on peak power, actually, turned out, because not all these applications necessarily completely max out their machines. And in a real data center where you have a mix of these kinds of applications running, you actually save more because they tend to exhibit their peaks at slightly different times.
That's a question about that.
Sure.
If you look at your power consumption now, how much of it is due to the fact that you have to over-provision or you're not scheduling as smartly as you might? That is, are there sort of quick software hits
So I think what you're asking is, could we manufacture complete idleness in our machines? And if you could, then you can sort of completely power down a machine or disable it and get it much closer to 0% load, where you're using a lot less energy.
Yeah, alternatively, could you execute at higher utilizations with smarter scheduling and wind up delivering decent response times?
Yeah, well, effectively that amounts to the same thing, because if you have a certain request load and you try to compress the number of machines you use to do that, then those machines will be busier and the other ones will be idle. And you'll end up with better scheduling. The problem is that often that is at odds with getting locality and sort of responsiveness in your system, because as you're shuffling things around and trying to bin pack things more during the lighter period parts of the day, for example, you end up kind of disrupting things. So you don't necessarily want to do that more than you really need to. Okay? The second area is kind of moving up a level. All of our production machines run Linux. This is basically fairly similar design to what was originally done in 30 years ago. It still works pretty well for us. We're pretty happy building our production systems on top of Linux. We have a lot of custom software that we run on top of it. But the design point of the original version of Unix is pretty far removed from where these very large data centers with thousands of machines are. And so this is this is our Oregon data center that we've just built in the last year or two. These are buildings with thousands of machines in them, fairly tightly coupled, so they have pretty good networking between them. Round trip times between machines are sub-millisecond kinds of level. And there's an opportunity to rethink what the base operating system running on these machines does, given that it's running in a cluster of thousands of other machines. For example, you could do remote paging to other machines' memory rather than paging to disk. That might be a more effective thing. People have investigated these kinds of things in isolation, but what would it mean to really rethink this, given that you're running on 10,000 machines with good connectivity between the machines? Performance isolation is a perpetual problem for us when you try to mix different applications on the same machines. Some processes end up consuming the buffer cache, and that's shared across different processes. And can you do a better job of performance isolation at the network and memory level, for example? So this is kind of what our current machine design looks like. It's basically a rack of commodity machines running. It's peeking inside one of these data centers. Is just rack after rack of these machines. I put in some pictures at night because it's, this is one thing we can do to save energy. A little bit. It's maybe a couple of racks worth of power for the whole data center to turn out the lights. So given these machines that we have built our systems on because of performance, price performance reasons, the problem is when you have lots and lots of them, you end up with all kinds of failure modes that you don't necessarily expect. In particular, one of our operations folks put together a nice list of what he sees in the first year of operating a new cluster. And
Definition of a cluster?
Cluster is kind of 5,000 to 10,000 machines that are tightly connected by sort of networking in the same building. So these are, some of these are planned, like we expect to move some machines. We have to move them because we need to get at a service panel or something. So we have to power them down with a lot of notice. Other ones are, the machine goes down and unexpectedly. Lots of disk failures. The trickiest ones are things that cause lots and lots of machines to suddenly drop off the network, because you really have to prepare your systems to deal with what happens when these 40 machines completely go offline with no notice. We have all kinds of reasons for long-haul networking completely taking out data centers, for example. All of these are actually true reasons that data centers have gone offline or network links have been disrupted. Blasphemy, the Pakistan government for a while tried to turn off YouTube in Pakistan. And so they basically did this by advertising a route to YouTube's DNS address that would black hole it within Pakistan. But then there was kind of a misconfigured router in Singapore that decided to take the Pakistan advertised IP addresses and publish them worldwide. So that was an interesting experience. Wild dogs, turns out they lubricate these cables with a lubricant that wild dogs like to chew on. Dead horses, you really bury your cables deeply, enough that if you're burying something, you generally won't hit it. But if you're burying a horse, that it turns out you have to dig pretty deep to bury a horse. And drunken hunters, apparently there were some hunters in Oregon. Most of our cables are buried, but you have some that are strung across poles because it's too hard to bury them. And apparently these guys weren't actually hitting any game, but they saw a big pole with something on top of it and thought it'd be fun to kind of shoot at it. So apparently the field ops people came back with something with like shotgun holes in it.
Sorry, I have one more question.
Yeah.
Is this steady state? That is, how much of this is infant mortality and how much of it is any year in steady state?
This is kind of the first year, so it generally gets a little better because you've kind of weeded out some of the bad actors. But you have enough hardware that it's probably a factor of 2 less events than this after the first year, I would guess. I'm making numbers up, but it gets better. You kind of want not the shiny new cluster if you're running your system. You want kind of the broken in one where most of the stuff has already happened, but it definitely doesn't go away. So, we do a lot of monitoring systems where you're monitoring various variables from low-level things about number of hard drive errors on this machine to higher-level application things like what is the latency of my most recent Gmail requests. And we kind of put together monitoring systems and pick out what we think are important variables and ratios of variables that we think are important. But there's an awful lot of raw data there that we're collecting, and putting together systems that can automatically monitor this raw data and observe what it thinks are interesting changes in the state of all these monitoring variables, and automatically figure out, oh, well, these 40 machines suddenly are unreachable. That probably means this rack switch is out, as opposed to sort of humans manually figuring this sort of thing out. For rack switches, we have monitoring in place that does this, but there's all kinds of other failure modes that are more obscure that automatic software could probably do a good job of. Or you could identify a case where this particular thing happened, and then in the future it can sort of find out the right patterns to look for that. And obviously, in addition to monitoring, you'd like to automatically adapt to this sort of thing. That's sort of a harder problem, but at least diagnosing and monitoring these things would be great. Another area where we spend some amount of time thinking and working on is building the right high-level tools and abstractions for building really large-scale computing systems. One example of this that we published a paper about a few years ago is a system called MapReduce that makes it easy to do pretty large-scale batch-style computations, where you have a bunch of data, you want to process it in some way, and you want to do it on lots of machines so that the underlying library takes care of a lot of the details of parallelization and what happens when machines fail. There's a lot of kinds of, and that works pretty well for a lot of batch-style problems, but there's a lot of more interactive systems that get built that we don't necessarily have as good a handle on building the right abstraction for that to sort of deal with a lot of the messy issues that MapReduce does in the batch world for more interactive kinds of requests. An example is, there's lots of things that have load balancers in between. So rather than sending a request from a client machine in our data center to a back-end service, we send it through a set of load balancers so that the load balancers have a better view of which are the busy machines in that service and which are not. It'd be nice if there were sort of natural abstractions that could do a lot of that kind of building of these distributed layered services for you rather than having people kind of more manually construct them. we've also more recently been building a lot of sort of client-side applications that have some amount of code running on the client, some amount of code running on the server. And are there better ways of constructing these than just kind of writing two independent pieces? Because you really want to kind of think about it as one integrated piece of code you're writing that happens to send requests back and forth as opposed to two separate pieces of code that you're trying to keep in sync. Another thing we worry a lot about is consistency. A lot of our services have per user data that they're storing, and the user kind of expects a consistent view of, even though they might be accessing that data from multiple different devices, their cell phone, their laptop. Their laptop might be disconnected for a while and then reconnect after they've updated some stuff. And even this picture is complicated enough, but the reality is you actually want to replicate their data across multiple data centers in different geographic regions so that you can keep that data available even if, for example, this data center goes south because of wild dogs or whatever. So being able to reason about consistency both between different data centers, between different consumer devices, between even different browser tabs on the same laptop is a useful thing. The main choice people make is you have kind of this strongly consistent model of the world where I commit an operation and then no matter where I read that piece of data from in the future, I'll see that committed right. And there's a weakly consistent model where you maybe have 3 copies of a particular piece of state, and you can commit an update to any one of them, and it will eventually be propagated to the other replicas. But if you read from one of those replicas in the meantime, you may not observe that committed right. Now, consistent operations typically have to be committed at a quorum of these replicas. So that imposes additional latency. And it's sometimes an acceptable trade-off, sometimes it's not. If it's not, then you move to these inconsistent operations. But then you have to, as a programmer, reason about, what do I do if I commit this operation and I observe an inconsistent view of that? Or how do I even know if I'm observing an inconsistent view of that? So as a programmer, it's certainly easier to reason about your application in terms of consistent operations. But if you want good performance, sometimes you need to move to these inconsistent operations. And even within single applications, we often use a mix of these different kinds of operations for updating different pieces of state. For example, when you mark a message read in Gmail, that just gets queued locally on your browser and eventually gets written to one data center. But in the meantime, if you get flipped over to a different data center, or you open your mail on a different browser and view whether that message is read, you may or may not observe the effect of that. But when you send a message, we actually wait for that message to be written sort of consistently to multiple data centers so that even if a data center gets blown away, that message will definitely be sent. And that's a trade-off that you make because this is a very common lightweight operation. It's not so bad if the user actually observes that the message wasn't read even when they've already read it. And this is a pretty bad thing to have told a user you sent a message and not actually ever send it. So there are 2 things I think would be useful here. One is having a more general model of these consistency choices that can help programmers reason about when they should use one kind of operation, when they should use another. Even when you have inconsistent operations, you still might want a knob that you can turn that affects the latency versus probability of observing bad things trade-off. So I think that would be kind of a useful direction to explore. And the second thing is inconsistent operations are not actually so bad to use if you have nice, easy-to-use abstractions for resolving what happens when you have consistent sort of conflicting updates and you need to resolve them. So thinking about, are there useful abstractions we can build that make it easier to write these inconsistently driven applications would be a useful thing. And you can view the 2 problems of what happens when a laptop resyncs with a they now reconnect to the network, and they now have some updates on both sides of the network. That's basically the same kind of thing, although a slightly different scale, as what happens when one of our data centers is partitioned, and then eventually that partition is healed because we repair fiber or whatever. Although the amount of data you need to transfer here might be much larger. The next area that actually I've been thinking about a lot lately is how can we build really large-scale systems that are sort of have a single instance that runs across lots and lots of data centers. Most of the infrastructure we've built at Google so far that people have built products on runs within a single cluster of machines. And then we have, over time, kind of built a set of tools that help us coordinate multiple instances of that infrastructure. But often those tools kind of solve one particular aspect of the problem when you need to run an application in multiple data centers. And then you have another tool that solves another aspect, and another tool that solves another aspect. And you end up with having to deal with a lot of internal tools to run an application that is spread across multiple data centers. And most of our applications need to be for fault tolerance and availability and latency. So we're sort of rethinking what infrastructure we really want in terms of running across lots of our machines. And these blue squares here are different data centers, some of which are connected to other data centers with nice fat pipes, some of which are connected by very thin sort of network links. For example, you rarely have enough bandwidth across the Pacific. No matter how, there's a lot of people in Asia, and then you have very little bandwidth from the west coast of the US to the Pacific in general. And so how can you build systems that are able to cope with this? You need all these different data centers to be able to operate sort of semi-autonomously. If any of these network links are kind of cleaved off, you don't want to completely lose access to operating on state and computation that is in those data centers. You need to be able to resolve what happens when you are able to reconnect. You'd like to be able to adapt to power conditions in these different data centers. So the real challenge is there's lots of these different dimensions you're trying to optimize things on. And a much more automated approach is what's really needed across different data centers. So that's why you need to build a single system that runs across the data centers, as opposed to having sort of developers or people manually sort of control motion of applications across data center boundaries. And you'd really like people to specify what they want rather than exactly where they want their data to reside or their computation to run. And because that will give the system more degrees of freedom in terms of moving data around to meet varying demands or conflicting needs across different application groups. So for example, right now we're working on a storage system that will let people specify for this kind of data or for this piece of data, I need it on at least 5 disks, 2 in Europe, 2 in the US, and 1 in Asia, as opposed to saying I need it in this data center in Atlanta and this data center in China. Or high-level SLA kinds of things, like I need the access time for accessing this data should be small. Another thing we sometimes struggle with is that there's a lot of potential applications you could build that, for example, if you're searching for something that's very obscure and other people in the world are searching for similar kinds of things, there are, how can you sort of effectively build systems that let people find out about other people they should really know based on their interests, while still preserving privacy in appropriate ways. So, there are a handful of people in the world interested in kite-based power generation, but the presence of data that you're interested in kite-based power generation is certainly available there. And how can you trade off building interesting services that let people connect in ways that would be useful while still preserving privacy and maintaining anonymity where appropriate. Another thing that has,
Sorry, just a question about that.
yeah,
This is pretty superficial. Are there concerns expressed by people that advertisements that you display have something to do with the content of their email?
certainly a few people have expressed those concerns. That's one example of something where I think, the ability to target things is sort of, some people find that kind of weird, and most people kind of say, oh, that's interesting. There's, advertisements because this email message seems commercial and, it's about someone's birthday and I have ads for birthday things. So I think, there are definitely trade-offs there that we make every day in building new products and deciding what features to add. And the right trade-offs are not necessarily always obvious in terms of what one should do. In many cases, those ads are quite useful to people. And so you could be providing useful service, but in other cases, maybe they're not what you should be doing. So another thing that has cropped up as we've developed more products that have a mix of private, kind of semi-private, and kind of broadly private with very large groups of people collaborating or participating in communities, and then completely public information, is actually building efficient retrieval systems that deal with documents in these various classes. So if you want to be able to search all the documents you should have access to, then it's pretty tricky to do that in an efficient manner if you have a mixture of documents, hundreds and hundreds of documents, some of which are shared with, each of which is shared with 10 people. So you have different people you collaborate with. If it was the same 10 people, it'd be pretty obvious what to do. You'd build a little index for the 10 people. But if you have thousands of documents you're working on, and each of them is shared with a different group of 10 people, then it's pretty unclear how exactly you build efficient retrieval systems that search all the information that a particular person should have access to, and do so in an efficient manner without incurring too many disk seeks or other kinds of overhead. And you should also probably search private email for that individual when they search, do a web search. And the other thing is that a pattern of sharing for a document might change over time. So you might add more collaborators to a document, or you might suddenly publish it to 100,000 people when you've finished working on it with your group of 10 people. And that might require a very different structure in your indexing system to deal with efficiently. Another area that is challenging is basically how can you automatically construct an efficient retrieval system that has the right sort of properties given a set of engineering parameters you're trying to meet. So in particular, when you're constructing retrieval systems, there's lots of different factors that contribute to how you want to structure things. In particular, how many updates do you need to deal with to the documents that are in the system? How many queries are you trying to handle in the system? How often do you need to update them? So not just how many updates do you need to do, but how quickly do you need to make them available in the actual visible, searchable state? And all those different factors contribute to different engineering trade-offs depending on what you're trying to do. You engineer a system very differently for a 1-second update rate than for something that can update billions of pages every 6 hours. And right now, we don't have a really satisfying answer. We basically have separate systems that we kind of put different classes of documents into for these different kind of classes of update rate and query frequencies. But it would be better if there was this kind of a single parameterizable system that would deal with the right engineering trade-offs, as opposed to having to build 3 separate systems to deal with these different kinds of classes of systems. We do have a common interface across all these systems, so that helps. So you can build sort of one scoring system or ranking system that runs on the different sort of abstracted documents, but has very different implementations underneath the covers for different trade-offs.
So I got a question
Yeah.
about this too. Maybe this is buried in your discussion of this or consistency or something like that. But for example, there's, the database community is always whining that, Google's this or Google's that isn't really a database system. We already thought of that stuff, okay? And in some sense, what you've done is to design systems that solve particular targeted problems at enormous scale. And it seems to me that there too, the challenge is, do you need to have disparate systems that solve particular problems in order to achieve that kind of scale? Or is there some common system? Maybe you're not talking here about a common system, though. You're talking about a parameter that would generate custom systems or something like that.
Yeah, I think probably you don't have a single common system because you do have different sort of data structures and different kinds of implementation techniques you would use. But it would be nice if there was a common parameterizable system that you could use that would use the right implementation under the covers.
Appropriate data storage system for a particular requirement. Yeah, got it. Okay.
Another thing that we have a number of projects in this sort of general area is that you want to be able to extract interesting sort of semantically understood information from semi-structured data. So basically, web pages have lots of structured and semi-structured data on them, but it's often sort of not fully labeled. It's not kind of semantic web kind of information where you know exactly that this piece of data means this piece of data is this attribute. Instead, it's in kind of HTML tables smeared across lots of websites with kind of common formats. And then there's some other information that's related to that on a different website. And you'd like to be able to extract this with reasonable precision and recall and correlate all this information across different websites, across different information sources, so that you can sort of combine together different attributes, different tuples about different entities in the world, and be able to correlate them, combine them, aggregate information, so that you can basically reason about actual data as opposed to doing kind of keyword search across pages that you don't necessarily understand the meaning of. So we do actually a fair amount of work in applying machine learning to various problems. And I'll talk about two aspects that we've found useful and think more work should be done. So one is a lot of machine learning algorithms can give you an answer, but don't really give you a very good explanation of how they came up with that reason, that answer. And it's actually quite helpful when you're trying to develop or use a machine learning algorithm if it can tell you why or what pieces of information it used in making this decision about your newly labeled data or your whatever it is you're trying to provide results for. To give you an example, it's much more helpful if it says, I think the probability of a user clicking on this document is going to be 73.2. It's much more helpful if it says, because this and this and this. So that helps you as a user of the system to find other features that you think might be useful to improve the accuracy more, or when it's not going well, to find cases, to find other features that the system could use to distinguish cases where it did well and where it didn't. So it basically helps you in feature selection for sort of future future revisions of the model. And the other thing is focus on sort of computationally efficient machine learning algorithms, basically algorithms that can scale to very large amounts of data. In a lot of cases, what the problems we have huge amounts of data available, and the problem is how can you run a scalable algorithm over it that will finish in a reasonable amount of time. A lot of the published literature is much worse than linear time algorithms and will not really be applicable for when you have hundreds of terabytes of data and want to apply the algorithm to it. So another problem that crops up in a variety of text processing problems is where we have done a pretty good job of exploiting n-gram models where you have a sequence of words and then you have built a probability model of how often that sequence of words is likely to occur. And traditional, for example, machine translation systems done 10 or 12 years ago used 2 and 3 gram models to help guide the translation process. So they would keep track of how often every 2-word sequence occurs in some corpus of training text. Or in some cases, they would push that to 3-word sequences. We've actually built systems that use 5 and 6 gram models of how often every 6-word sequence occurs in all English documents we can get our hands on. And that has led to significant increases in accuracy for machine translation, because you can use these 6-word probabilities. If you have a couple of translation candidates, you can say, well, this one has a 6-word sequence that has occurred 3 times in English documents, and this one has a 6-word sequence that has never ever occurred in 20 billion documents. So it's pretty unlikely that I should use that phrasing as opposed to that one. It helps you distinguish, the priest of agriculture versus the minister of farming or something. The real challenge, though, is that these are very localized methods. So they help you in a relatively small window. And if you try to expand that window, you end up with this incredibly large combinatorial explosion of possibilities in what information is actually important to consider when you're deciding should I use this translation candidate or this one, and what is just kind of irrelevant noise. And if you think about the process of a human translating a lengthy article, you want to be able to know that I should use this word here because I used it in the paragraph above, and I should use the same word because it would make a lot more sense to a human to use the same word there as opposed to a different word that means the same thing. And how do you separate that from an irrelevant detail like, I phrased it a little bit differently, but it didn't matter, that kind of thing. And this has applications in a lot of areas of machine translation, speech recognition, natural language processing, and so on. And there's actually lots of interesting systems problems in this same space in how can you actually build these very, very large language models in a scalable manner that you can actually get the lookup bandwidth you need in terms of translating systems. For example, our machine translation system needs to do about 1 million lookups on this 5-gram model per sentence it translates. And that model fits on 200 machines or something. So interesting systems problems. And kind of related to the previous one is how can you build speech recognition systems that are less brittle. So speech recognition systems work pretty well when they're trained on data that's very similar to the kind of data that they're seeing. The big problem is that if you have slight acoustic differences in the model at the low-level acoustic models, or you have slight differences in vocabulary at kind of the higher-level word-based models, then the recognition accuracy goes way down. For example, if you have a system that's been trained on broadcast news, you get about 15% word error rate. But if you look at kind of news-like broadcasts that are published on YouTube, then the accuracy drops significantly because of different acoustic conditions, slightly different vocabulary models, and you end up with 30 to 40% word error rate, which is pretty unintelligible, whereas that is, much closer to intelligible. And so there needs to be some way of improving the robustness of these systems so that they're not quite so brittle in terms of the training data that they've looked at. And a final problem is in the area of computer vision. So there's lots and lots of interesting data being that is more and more available. That people are posting images all the time to the web. The amount of video data being posted and available is increasing exponentially. And there are a lot of image processing algorithms that work pretty well in restricted domains. So for example, face detection, OCR is actually kind of a vision problem. Those kinds of things tend to work pretty well. We actually launched a product now on Picasa that when you have a bunch of photos, it will cluster faces it thinks are the same person, and then you can label that face once. And so that in that kind of restricted domain, this kind of thing works pretty well, and it's pretty remarkable actually, because you see a whole cluster of people all that are the same. It says, I think these are all someone, please tell me who this is, and then in the future it will label future photos of that person with that person's name or whatever. But we're pretty far away from being able to look at an image and generate what any human can do today, which is to say, oh, that's a brown horse in a meadow, right? But there is substantial training data available. The way Google image search works is not actually by looking at the images at all, really. It uses text surrounding the images to generate what it thinks is a summary of the image. And that works pretty well. Sometimes the text actually has nothing to do with the image. But for the most part, that text actually is descriptive of what's in that image. And that means you have billions and billions of training data, pieces of training data available that say, for this image, it's a brown horse, and that kind of thing. And given enough of that data, you should have a good enough raw base to start building systems that can look at all that training data and try to recognize images that they've never seen before. So what I think the overall conclusion is that there's been tremendous increases in user connectivity to the internet, people putting new information available online in all different forms, web pages, images, videos, bringing other kinds of information that weren't previously online, like scanning books and making them searchable, and a tremendous increase in the computational power available to process all this information have created a bunch of interesting new problems. And I think the nice thing is that a lot of these problems are such that we don't know how to solve them, that they are actually really hard, but they would be very, very useful to be able to solve in terms of making better products, making people's lives better. And the kinds of problems I enjoy working on the most are ones that kind of span lots of areas of expertise. So it's not the case that one person can solve this problem. They need a collection of people to work with that have different complementary areas of expertise to sort of all put their thinking hats together and come up with solutions to the problems. So, questions, thoughts? Thanks.